Taught both my children how to write in cursive. I think it's a very good skill to have because not only do you learn to write a signature, but if you ever do, and actually I think it refines your normal handwriting better. Because my son, his normal handwriting is horrible and you need a key to translate it, but his cursive is immaculate. It's beautiful.
Yeah, I think it's a good skill, and
I'm like, what went wrong?
Lots of things to talk about, but I'm going to try and get my kids to learn it.
I was like, what happened to the theory? It didn't help your handwriting any, but at least you can write cursive.
At least you can write cursive.
He's like, I type everything. Nobody needs to see my handwriting.
Yeah, whatever. Wait till you do math. You're not typing it.
Actually, his math is very nice. He's very good about his math. But
that's good.
Nope. Stop. Go on. Ow. Ow. No, my shoulder. Go on. I put my hand back to the back of my car this morning and I heard a pop on my shoulder.
Oh, that's no good.
Oh, I can't turn my arm around now. What?
All right. So what do we have questions on today?
No, because you haven't eaten dinner. Go. Oh, I had a question on number 4 on assignment 13. I was lost. I tried to figure it out online. All I figured out from the solubility chart is that Na2CO3 is insoluble. That's all I got.
It's a little soluble, but.
Well, nothing is completely insoluble.
Right. As we are learning.
I couldn't figure out how to answer the question because I didn't understand.
Okay. So let's share it.
And then another easier question after that. It's like a 5-minute thing.
You never know.
Well, I hope it's a 5
This one might be an easy question too.
Oh, God.
Okay, so you were talking about our contaminated wastewater pool that has cadmium in it. So in this particular scenario, you can make aqueous sodium carbonate. So that's what you have. You have aqueous sodium carbonate, aqueous potassium iodate, and aqueous potassium sulfide. So when we're talking about precipitating these reagents out, the first thing to think about is probably like, what would we be making? So what might be a balanced equation? So we have cadmium, right? Presumably it had some kind of counter ion, but we don't really care what it is. So if I'm making reacting cadmium, what is it going to combine with in these 3 different scenarios? What are we going to make? We got to remember our precipitation rules. But I made it pretty easy because this is a cation, right? So is the cadmium going to combine with a cation?
No.
No.
Anion.
It would combine with the anion.
So what are our anions?
CO3.
The CO3, the
Uh,
IO3? No. Would it be IO3?
2 minus.
And the S, right?
Oh.
Okay, what are the charges on these guys?
Oh, God.
That would be just a -1 on the IO, and then that would be a -2.
All right. And McKenna knows these because
so if you can tell by the cation, whatever that charge is, you know that sodium has just a plus charge. So since that has a 2, then you know that it's a -2. Is that what we're clarifying? And then, yeah, so on and so forth.
Yeah, so these guys are all in the same column, and they're in the first column of the periodic table, and all those guys make +1 charged cations. So it's coming back, right? It's coming back. All right, so if we have cadmium 2+, then what's it going to potentially make? What are the 3 compounds that we could make?
CO3.
Yep.
Then
IO3.
Yeah. And then
1, 2.
It would be a 2 to, yeah. And then CD2S.
2.
No, it'd be
Right?
CDS. No, because 2
Yep,
plus 2
that-
minus. I had to think about that for a sec.
Yep. All right. Good, good, good. So we made these 3 compounds, and so presumably we want to try and precipitate them. And so what we're going to look at is we're going to look at the KSP equations and the KSP values for these 3 compounds and find out what they're like. So
I have
if
one of
these-
those. Hold on.
if these guys are insoluble, then they'll have a KSP value. And depending on what their KSP value are like, we can.
Cadmium carbonate is 5.2 times 10 to the negative 12.
Okay, let me make some space here. Say that again.
5.2 times 10 to the negative 12. I don't know if this site is right, but that's what I have for at 25 degrees Celsius.
Okay.
I can't find the cadmium. I know where the cadmium sulfide is. The cadmium sulfide is 8 times 10 to the negative 28.
Okay.
But I
So
can't,
these are all in the back of our quantitative analysis book in the tables there as well. So if you can't find iodate in the table you have.
actually, I had a problem with this table in the back because I couldn't find a lot of stuff on here.
So it is a challenging table to use. Let's go ahead and take a look at it.
Cadmium iodide.
Can I ask a quick question
Mhm.
on what? So when you say the KSP, is that of the anions,
The KSP is of the compound.
the compound? Okay.
So this
I haven't got
table,
to that video yet.
this table is organized by the anion. So all of the carbonates are together. And so we would find the anion first, and then we would go and see if we can find the compound that we're looking for. So like calcium carbonate has 2 different forms. Down here, here's cadmium. But it's a little funky because they all say L equals, and that's sort of awkward.
Oh.
So this is how to read this particular table. We have our name of the anion, and then they tell you what exactly the anion is,
So
what the formula is, and then you find your cation on the table. So here's the cadmium
6.
carbonate, 1.8 times 10 to the minus 14. That sounds pretty similar to the one we had.
Yeah, sorry, I was using another website because I was having a hard time with this one.
Oh no, it's okay. I'll just update it. So that was 1.8.
Times 10 to the negative 14.
Thank you. Okay, so there's carbonate, and then chromate, cobaltous cyanide, all kinds of ones in no particular order. Hydroxide, we didn't have hydroxide, right?
No.
Okay, iodate, here's iodates. So here's our iodate, 2.3 times 10 to the minus 8. And then sulfide. Here's the sulfides. So they have 1 times 10 to the minus 27. So not too different from the one we had.
See, now I understand how to read this thing because it was really confusing.
Exactly. It is a pretty confusing table. There's lots of useful information that is sometimes a little hard to navigate. All right, 1 times 10 to the minus 27. So these are the 3 KSP values. And when we are thinking about how to handle the KSP values, why are you not giving me the eraser? That's weird. These KSP values are describing the equation, which is this solid, each of these solids, dissolving.
Okay.
And so it's telling us what the K value is for this reaction to go forward. So each one of these compounds, I can write a similar kind of equation, and we can see these 3 K values. So what are they like relative to each other?
Well, the CDS has the lowest, and the cadmium iodide has the biggest.
Yep, they're all small. So none of these reactions go forward very well, but the cadmium sulfide reaction is the least soluble because it has the smallest K value. So this is the least soluble of the 3 scenarios that we have. So if we're trying to precipitate the cadmium, which one of these are we going to want to use?
The iodide one, right? Because it's the biggest number.
Do we want it to dissolve or not dissolve? Because this is the reaction
Oh,
to dissolve the
we
solid.
don't want it to precipitate. We don't want it to dissolve all the way.
We don't want it to dissolve at all, right? We're trying to get the cadmium out. So with these KSP values, it's always like kind of the opposite reaction of the one that you're used to thinking about. The KSPs are to dissolve a solid, and so the smaller that number is, the less soluble it is. The more it's going to stay as solid and not dissolve.
So it would be the sulfide, because that has the
Mhm.
biggest number, or smallest number,
Smallest
biggest negative value.
Exactly. Is that clear for everybody?
Yes.
So it would be a solid on the other side of in the products, the KDS, cadmium
So
sulfide.
the way that we would write it, yeah, is that we put the solid over here on the reaction. Oh yeah, and if we were doing that initial precipitation reaction, Na2, oh, excuse me, it was not Na2, it was, this one is a potassium sulfide. So if we were writing that initial equation, then yes, this would be a precipitation reaction to form solid cadmium sulfide, and then we'll have some potassium iodide, or some potassiums left over.
Potassiums. So when you write the equilibrium constant expression, the solid doesn't go in it, right?
Mm-hmm. That
So
is
it would just be these 2 guys on the left up top, and then one on the right, on the far right, on the bottom.
so this is not the equilibrium reaction.
Okay.
This is a precipitation reaction.
Okay.
So the precipitation reaction is what happens first.
Okay.
The equilibrium reaction is what happens next. So in the equilibrium reaction, we're just looking at this guy. And we're saying this cadmium sulfide, it's a solid, but a little bit of it could dissolve. And here's the K value. For this reaction. And this is actually really super important. So I want everybody, just in case you are not totally tuned in, I want to make sure you really super duper pay attention to these 2 parts.
Okay.
Because we often have something like this going on in our equilibrium reactions. We'll have some kind of reaction that happens first, like a precipitation reaction or an acid-base reaction or a redox reaction. Something will happen. And we'll have some stoichiometry that's involved in that reaction. Then, after that initial stoichiometry reaction is done, we will have a second reaction that is the equilibrium reaction. So I want you to be really, like, write yourself a note or something like that and ask yourself, which is my stoichiometry? Am I doing stoichiometry right here? Am I doing some kind of a precipitation reaction or an acid-base reaction, that I need to like deal with that chemical reaction first. Now I'm going to take those products and I'm going to do an equilibrium reaction with those products. So I want you to just really like, I don't know, write yourself a flow chart or something that says, or a checklist. What am I doing in this step? What am I doing in this step? And make sure it's super clear. Because this is one of the really common mistakes that I see when people are dealing with equilibrium problems, is that they'll get them sort of mixed together. So try and be really clear about what's going on.
Okay.
Hey, can you explain one more time why the smallest K value would be most successful for the participant? Yeah, you know.
Yeah, absolutely. So let's draw some pictures. So we have cadmium sulfide. And this K was, I'm just going to write the 10 to the minus 27, I think it was, or was it 28? I forget.
27.
And then we have, thank you, carbonate, which was like minus 15, I think. And then iodate, which was bigger, minus 7, minus 8, 14, and minus 8. Okay. All right, so we're just thinking about the order of magnitude that each of these guys are. Each one of these is, we're talking about how much this is going to dissolve. And so our equilibrium constant expression for each one of these is going to be, because it's got a solid on the other side, it's just going to be the products. So each one of our K values tells us about how well we make products. And so since this is really tiny, and this is pretty small, and this is not
Bigger?
pretty small.
Well, it's bigger than the smallest one. Maybe say bigger. It's still small, but bigger.
Yeah, right? So this is teeny weeny, and this is hardly noticeable, but bigger than teeny. And this one is still small, but there. So all of these are saying how much products we're gonna make, right? That's what this number is about. It says how well we make products. And the answer is not well in any of these cases. However, this one is the worst at making dissolved products because it's so small. And this one needs a 2. And this one is not great at making products, but you would be able to measure it without too much difficulty. Does that help you kind of conceptualize?
Yes, that's perfect. Thank you.
Mm-hmm.
Can you go over 4B as well?
Yeah,
Thank
absolutely.
you.
So lower solubility means better precipitation.
Mm-hmm. Yep. Yeah, because we want to have it all fall out of solution and sit as little rocks at the bottom so we could filter it out.
And I was actually going to ask that same thing. I was like, can you do B?
Mm-hmm. Of course. All right. So what do we need for us to do this kind of a reaction here? So we have two scenarios, right? So just like we talked about a minute ago, we have 2 steps. We need to pay attention to our precipitation step, and then we need to pay attention to our equilibrium step. Okay? So let's take care of our precipitation reaction first. So what do we know about this precipitation reaction? we can write a balanced equation, right?
Yes.
Yes.
Currently, this sounds like a solid. So it's going to dissolve when we throw it in to our pool.
Mm.
Okay. So we have an initial concentration of the cadmium, and we have a size of the pool. And then we have a number of kilograms of the potassium sulfide. So what do we want to do first? Strategically, you are not sure.
Oh, I was getting stuck. I started converting to moles, and then that wasn't really getting me anywhere. And
Well, let's start with that anyway.
okay,
Moles is always a good plan. So let's, if you don't know what else to do, get to moles.
Yep.
Which one do we want to get to moles first?
So the 0.010 moles per liter times 8,000 liters.
Sounds good. So we're dealing with the cadmium first.
I got 80 moles there.
Sounds good. Do we have a confirmation?
Yes, I got that.
Cool. We probably only have 2 sig figs here.
And then I started converting to 15 kilograms to moles.
Okay, so we'll convert 15 kilograms. All right, so we need it to be grams. I hope these numbers are good. I just kind of threw some numbers around and said, I'll figure it out later.
Like, see, I got 110.262 grams of K2S per mole.
110.262.
Yeah.
All right, we have confirmation on that one?
No, I don't want that.
I don't have a periodic table handy. Let me look one up.
I got that as well.
Excellent.
Wait,
All right. 32 plus, sounds reasonable, plus 40 times 2. All right, so that's going to get us moles. So how many do we have? Like 150 or something? Let's see, because that's almost 10.
Uh, 136. I got 136.
Hold on. So we're taking the 15,
Got the
timesing
same.
it by 1,000 and then dividing it by 110.
Mm-hmm.
Yeah, 136.
Cool. All right. So this is the amount of cadmium. This is the amount of sulfide. So what's our limiting reactant here?
It's gonna be the cadmium.
Okay. So we're going to use all of the cadmium, and we're going to have some extra. Cool. So let's figure out how much extra we have. I am teaching. We're just having a quiet moment while everybody works.
So don't we have to put it into the X equation, whatever that is underneath for the change?
No, because we're not yet at the equilibrium. We're just still doing the stoichiometry. So if we're reacting cadmium and sulfide, how much sulfide is left over?
54 moles.
So 136 minus 80, right?
Yes.
So, excuse me. Cool. All right. So now we're ready to think about our port 2. All right, so our equilibrium is always kind of what happens next. So let's draw a picture. So we have in our 8,000 liters, we have made a pile of 80 moles of cadmium sulfide, right? It's quite a pile. But we have 56 moles of potassium sulfide still left over. And this is now aqueous because it's dissolving in our 8,000 liters. So we really have the stuff we care about is we're going to have some concentration of sulfide, and then we're going to have a big pile of cadmium sulfide. Okay? So what is this value?
Point 0.7.
Okay,
Zero
point,
point. Oh, 8,000. Sorry about that.
okay.
Yeah, 0.007.
Okay, so this is 0.0070 molar, and this is solid. So, all right, where's my cursor? Yeah, down, go down, little guy. Thank you. I need more space. Okay. All right, so what's our equilibrium reaction like? We have,
It's KDS solid
Plus KD2 plus S.
gives you, yeah, KD2 plus and S minus 2.
great. So we are ready for an ice table,
Okay.
and we don't need to worry about the cadmium sulfide right here. So how much cadmium do we have currently dissolved?
1 mole.
We do? Did we have some left over?
No.
No, we used all the cadmium.
Yeah, so how much do we have?
0.
0. Okay, how much sulfide?
0.007.
All right, Ronan, go check on the ducklings, please. Okay, what direction is this reaction gonna go?
Okay.
Gonna go forward.
It has to go forward, right? We can't
Yeah.
take away from 0. So it's gonna go forward some amount. And then at equilibrium, we're gonna have X, and we're gonna have 0.007 plus X. Right?
Mm-hmm.
Okay, what's our equilibrium constant expression?
Product.
It's K equals the CD2 plus concentration times S2 minus concentration.
Mm-hmm. And that was 1 times 10 to the minus 27. So let's plug it in. We have X, and we have 0.007 plus X.
So if you say forward
Mhm.
over, oh, so we don't have the solid under because,
It's solid, and it doesn't show up in our equilibrium constant expressions.
okay, got it.
Okay, so now we got a number. 1 times 10 to the minus 27 is equal to x times 0.007 plus x. So that's really like this plus this. Now, we're going to try a shortcut.
X.
And the shortcut is we're going to try it both ways. We're going to try our shortcut and then we're going to do it the whole way. And we're just going to see how different the answers are. The shortcut is to say, this is not very soluble. So I don't think that our decimal places on the cadmium sulfide are going to give us enough sulfide back again that we're going to have decimal places that are going to have a significant difference compared to 0.007. So we're just going to approximate this as 0.007 instead of worrying about the plus x. And that way it'll make our math a little bit easier, and we're just going to try it that way. Okay? So if we go 1 times 10 to the minus 27 is equal to, and we don't have this little x here, it's just going to be x times 0.007, and that's all. And so we can just solve it. Okay, so 1 times 10 to the minus 27 divided by 0.007.
It's to the negative 25th. It's 1.43. Well, actually, it's 1 sig fig, isn't it?
Yeah,
So 1.4.
yeah, you could probably go like that. Okay, so that's small. That's not very much cadmium that is left dissolved, that is present. So let's try it the whole way. So this you can write out as a quadratic equation. And solve it that way. Or you can pull up Wolfram Alpha and type it in and hit solve.
Hold on a sec. How did it become x squared?
This little guy right here. This is our non-shortcut route.
I get.
The x squared was because this is an x and it has to be multiplied by both of those guys.
I get it. My algebra brain went, no.
I'm just pretending that it's not there. La, 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 la. All right. I'm going to let you work on. Check on some noise.
Wolfman Alfred.
Oh, good. All is well.
Hey, on the Wolfram Alpha, how were you doing the times? Were you using an asterisk?
Mm-hmm.
Okay.
Wait, is it times or plus?
Well, there's 0.007 times x, but on Wolfram Alpha, you should be able to just type 0.007x.
I noticed between your parentheses, you're doing times. I couldn't figure out which button you were using. Okay. Thank you.
I got like negative 0.007, so I don't know if that's right.
You mean for your answer from Wolfram Alpha?
For x, yeah. X squared plus x minus 1 times 10 to the negative 27. I don't understand why it's having problems.
Probably because this one is so small.
Maybe parentheses might help. No, I still get the same number. So I don't
It
understand.
may be having trouble because it's such a small number. Because we can't get a negative number. That's not.
Yeah,
gonna-
that's the number I get. Same thing, Ashley.
I did it by hand and that's what I got. And it doesn't make sense because it's negative.
right.
What is that?
The quadratic equation.
Oh. Are we supposed to do the quadratic?
You don't have to, but if you're doing it by hand, you can do it that way. Oh, that's too many zeros right there.
So do we not, I mean, is Wolfman out, oh, is it wrong?
Well, we can't get a negative number. So probably what's happening is it's giving us a different root, and we just have not been able to tell it to give us the other root, that our differences are so small that we're having a hard time with it. Yeah, it's my calculator is having a hard time giving me that small of a
Is the
difference as well.
shortcut a better option?
Shortcut is a better option for this scenario, yes. So, and this is one of those scenarios where you will have to practice a few times to know when you can use the shortcut and when you can't use the shortcut. But I will say that we're just going to cross this out for right now, that this usually works if the K is relatively small. It's only when the K is kind of large that you have enough dissociation that you can't use the shortcut. So the shortcut is handy in that way that it's almost always right, and it's also easier. So why would we not want to do it, right? So what we did with our shortcut, just to be super clear, is that when we were looking at this second ion, because we have a lot right here, and this is going to be very tiny, we're saying this is not going to be so big that it's going to affect the thing that we have a lot of excess of. And so we're just going to go with the approximate answer that's going to be plenty close enough, because it makes our lives easier, and because we have a hard time getting our calculators to tell the difference between these very, very tiny difference.
So the x squared goes away.
So the x squared goes away. Yep.
Because the amount of sulfide is so small.
Yeah, because the amount of sulfide is large compared to the amount of cadmium. So I will rewrite this to make it less messy. So we had sulfide and we had cadmium. And we said initially we had 0 of this and we had 0.007 molar, which doesn't seem like a lot, but it's a lot bigger than 0. So our change was plus x, which is very small. So at equilibrium, we have x, and we have approximately 0.0070 molar because this x is so small. So then in our K value, our K equation of cadmium and sulfide, this is just x times a number. Cool.
Okay, leave them alone. Okay. So in that question, I got a little stuck on number 3 trying to do the balanced equation. I got the equilibrium equation, but the precipitation equation I was having an issue with. And setting up the ice table.
Okay, we don't actually have a, I don't think we have a, for problem 3,
Yeah,
we don't have
because
a,
you said balanced equation. Does that mean,
yeah, how it dissolves in water. So that's the one like this.
yeah, that's where I got, oh wait, so that's, oh, confused.
Okay, so, oops, I'm still on cadmium.
Calcium, they're both C's.
Calcium. Hold on a second. Sorry. More duck drama. All right, so what's calcium hydroxide going to dissolve into?
Ca2 plus OH minus.
Does that look
Yeah.
good?
But that's the equilibrium. Is that what we're looking for?
Mm-hmm.
Because I thought
Balance.
when you said balance, you meant the other.
No. There's lots of different balanced equations. This is just the one thing dissolving into water.
And then the ice,
Just a second. Sorry, there's weird noises in our neighborhood tonight.
because to answer B, you have to have the ice table, right? To figure out your molarity.
Yeah, so we will need to figure out how much calcium will dissolve, which is going to be based on this equilibrium. And then after we figure out what number of, what the molarity would be, then we would have to work our way backwards to grams of calcium hydroxide.
And that would be the molarity of the calcium. See, that's where I got confused. I got to the molarity. I finished the ice table and I got to the molarity of the calcium.
Great. And it's going to be in 1 liter. So you got a molarity. What was it?
1.17 times 10 to the negative 2, but I don't know if that's right.
Okay. Well, we'll just roll with it. So if we want to get to grams, then how can we get to grams from molarity?
You would have to divide by the molar mass.
Well, you'd have to multiply by the 1 liter to cancel out the moles per liter. And then from the moles, you would have to divide that by the molecular weight.
Right. So we have 1.17, because I made it easy with 1 liter, mole of calcium ion, which means how many moles of calcium hydroxide do you have?
1, because it's 1 to 1, right?
You have 1 to 1, right? So we have 1.17 times 10 to the minus 2 moles of calcium hydroxide. So now we can go to grams.
The mass for that was really high, I think. Okay, my periodic table disappeared on me. Where is my...
I gotcha.
Calcium is just 40.078.
That's what I was looking for. I had that pulled up on one of my tabs, but I don't know what happened to it.
Keep the tape to the wall.
Yeah, I have one on my wall back in my office at work, and then I don't have one here. I don't even have my periodic table throw blanket in here, so.
So I got 74. I don't know if that's right. Anybody else
Ah.
get that?
Looks right.
Okay.
$74.09 grams per mole. So moles. $74.09 grams per 1 mole.
Wait. Oh. Yeah. Okay. Now I gotta try to that number times 9. Like 0.867
Same, yeah.
or huh, what?
I got that as well.
Okay. So assuming that this molarity is correct, then
Well,
Are
I
we-
mean, when I set up the ice table, I ended up with it
Mhm.
being the KP equals 4x to the third because one's
Mhm.
x and one's 2x.
mhm,
So I just divided by 4 and took it to the 1/3 power.
that seems reasonable.
So, and for C, it's just as simple as taking that KP value and then it's it would be X for the CA2 and then the molarity they give you squared, right?
Mhm,
And so you just divide by that square value and you get your
mhm.
molarity.
Yep, that's correct. So we have K is equal to calcium 2 plus and then hydroxide squared. And this is the number from the table. Hey, that square didn't go in there. This is the number from right here inside. And we just solve here.
I mean, I hope I did the ice table, right? It's simpler than the other one with like the having to go around and do it a different way.
I'm sure you did.
Ice tables are fun to play with.
Mm-hmm. It's interesting because I don't remember being taught ice tables when I was learning chemistry.
God, my teacher drilled ice tables. That was the only way she made us do our things. Like every time we did one, it was do an ice table, do an ice
Yeah,
table. It's like,
yeah.
even if you could go around it, she's like, no, do an ice table.
Yeah, it's so organized. And so, and I don't think even that the first time I taught equilibrium, I don't think our book used ice tables. And so it was a couple iterations down the road, and then I saw it and I was like, where has this been all my life? This is so wonderful. I love it. All organized and tidy.
Well, and it helps people like me who are a little dyslexic. can put our stuff in the right places.
Exactly. Yeah. No, it helps organize. It keeps everything kind of lined up. It's, systematic. And when I'm learning something new, I know that doesn't necessarily work for everybody, but when I'm learning something new, I want it to be a procedure. I just want to be able to follow a flow chart and just have a number pop out if I follow the process right. And ice tables are like that.
So if you roll back up down to where you did 4B, the units at the end of that would be molarity, right?
Yes.
I didn't put my units in. I just realized. It's like, no.
Yeah, we have to.
It erased itself.
It did. I'm sure it saved itself too. I'm recording it. Don't know how it could have erased itself, but
Oh, there it is.
there, it just moved down.
So it'd be the molarity of the cadmium 2+, or you could just put molarity, or do we need to put the cadmium 2+?
So I would put molarity and I would put cadmium 2+.
I'm running out of space.
Can I ask a question?
Of course.
I don't know if we're ready to move on or not, but on assignment 12, number 5, I got through the whole assignment and then I got to number 5 and I didn't know how to start it, I guess.
Let me pull it up.
Oh.
Oh, okay. This one is easier than you think.
Okay.
This one is really just about using Einstein's relationship, E equals mc squared. And we're just really going with this approximate 0.2 grams for the mass. And then we just need the speed of light squared.
That's the mass difference, right? So that would be where the, okay.
That's all we have to do on that one?
That is all you have to do on that one.
Well, you have to
All
convert
right.
kilograms
Good.
instead of grams.
Yeah, I mean, there's a little bit of unit conversion,
But that's
but
it.
not too much.
Because joules requires that you have kilograms.
Exactly.
I have a question also about number 4. I'm sorry. Hang on.
Mhm.
Sorry.
Please. On this assignment? Was that Maria?
No, it's Erica. Sorry.
Sorry.
The same homework assignment, number 4. I know that we talked about it, I think yesterday, but I'm still confused about the mass difference from what we calculated versus what was given in the web elements table.
Sure. So we're looking at bismuth and iron. And so we needed those two charge numbers as well as the mass numbers. And let's see, iron is 26th and bismuth, where is bismuth?
BI.
Yep, BI.
Where's
There it is, 83, thank you.
Yeah, there we go.
26 and 83.
83.
All right, 83 and 26. So when we do this addition, the main number that we're looking at right here is the sum of these two numbers, because that's going to tell us what element we're making, assuming we're making just one element, but I told you that's what we're going to do. So we've got 83 plus 26, which gets us 109 for the number of protons. And so 109 protons is meitnerium. And when we look at meitnerium a little bit more in detail for its isotopes, We have between 265 and 276 for our mass number for possible isotopes that we could make. So if we go back over to the assignment, this is Meitnerium, and we have between 265 and 276, I think I said, for our possible range. So 209 plus 58 is 267. So we could make a 267 Meitnerium, and then we've used up all of our particles and we don't have any mass left over.
So that top number is the mass, and then the bottom one is the atomic number?
Yes, yes. So this,
Okay.
the mass number is the number of neutrons plus protons for each of these elements, and it's called the mass number.
Got it. Okay, I think I was just confused because I saw that in the web elements table, the mass value that they gave was the same as the isotope number. So I thought that we had to fix the mass somehow, and I wasn't sure how to go about that.
I'm not sure where you were looking, because all of these guys, they only show the mass number. It's the upper left.
Oh, so yeah, I was confused. I thought the mass number that we know now was the atomic number, and then in the column over, that was the mass that the element had, but obviously that's not correct.
These are the masses. So the mass number is the number of protons and neutrons. That's the integer number. And then the atomic mass is usually pretty similar to the mass number, but because the mass of a proton and the mass of a neutron is slightly higher than 1 gram per mole, the numbers don't exactly match up. So like the 265 Meitnerium has a mass of 266 to the best of their ability to measure it, right? And this 266 Meitnerium, they also seem to have 266 because these guys are only around for a little tiny amount of time. And so the ability that they have to accurately measure the mass is pretty poor. So this one probably isn't very correct. It might be a typo as well, since the other ones are all pretty similar. That's what they are supposed to be.
Oh, they did bad. They made a typo.
Yeah, they might have made a typo right there. Yeah, that could be a typo, but I don't know because I've never looked up the IUPAC details. So.
I got a question about the lab. Are we just graphing it the same way? Just the 1/x and the natural log of, I guess, temperature?
So this one we don't need to do any fancy graphs for. We just need to graph it versus time. So if we are...
It's, wait, temperature versus time?
So we're just looking at, come on, I said give me a pen, come on. I don't want a shape, give me a pen. Thank you. All right, so we're just doing temperature versus time. And depending on what kind of a lamp you're using, you may end up with kind of a linear relationship, or you might end up, if you're using a hotter lamp, you might end up with something that looks like this. You may end up with something that goes up and then plateaus. So depending on the details of your experiment, you will have a variety of different shapes available for your graph, but the details are mainly that hopefully you're going to get some temperature increase as you.
So if you decide to use canned air instead of vinegar and baking soda, you just don't do the mixing part of the lab. You just squirt the canned air in there.
You just squirt it into your container.
So in the instructions, it says go for 5 to 20 minutes until you see it plateau. But if you did a linear one, do you just stop at 20 minutes?
Yeah. Most of So all of the experiments that I saw, I did see some amount of plateauing.
Okay.
And that's
But-
what we're looking for, right? Plateauing.
I guess.
So, what vessel are we supposed to use? Or I didn't see that in there.
Like bottle or bag. There's lots
So-
of options here.
I used a 750 milliliter plastic soda bottle the first time I did it. And then the second time I did it, I used a 1 gallon plastic water bottle. If you have colored plastic, you can try that. If you have a glass jar, you can try that. If you want to use a Ziploc bag, you can try that. Just
But
make
how do
sure.
you keep it from leaking? Because you're gonna have to stick the thermometer in there for the temp, aren't you?
Yeah, just tape around it.
Oh, okay. So try to make the best seal
Mhm.
possible.
Yeah, and I was amazed. You can use Play-Doh if you have some Play-Doh.
I got plenty of that.
I thought you might have some.
Air dry clay, I have that too.
Yeah. So there's lots of, creative ways to make an airlock. The first time that I did it, I just drilled a hole in the top of the bottle. Like I pounded a nail through, and then I made it a little bit larger in the cap of the soda bottle. And then with the plastic water bottle, I just poked, because the thermometers you guys have are kind of like meat thermometers, and I just poked a hole in the side of the water bottle, and it worked just fine. It made a nice tight seal.
Seconds.
But if you are concerned about leaks, then just put a little Play-Doh or a little tape. It should be fine.
Are we doing a comparison between like a bag and a bottle, or like?
No, so you're going to choose the same, you're going to do the same container except for one variable that you are exploring. So if you want to use a plastic bag, then you will do air in a plastic bag, and you will do your greenhouse gas in a plastic
Oh,
bag.
okay. That's what I was like. Wait, hold on. That part was confusing. Okay.
Yeah, if you want to do a plastic bag with a piece of dark paper inside it, then you do air with a plastic bag and a piece of dark paper inside it, and you do your greenhouse gas in a plastic bag with a piece of paper. So your variable is different, not between the two experiments that you do.
But
Your variable
between-
is different between your experiment and other people in this class, because after everybody does this experiment, we're going to have a conversation about
Okay,
what kind of results we saw.
that makes sense. So if we do temp over time and we do get a curve, do we just scatter plot and try to find a trend line?
We just need a start and finish.
Okay.
We just need all we really need is we need a change in the temperature.
And then you want the standard deviation and the mean. which-
Yeah, because I want us to do replicate measurements so that we can feel convinced that if we did it one time with just air.
That's
and
why
we
you
did
said do
one
it 3
time.
times. So we'd have
Right.
3 runs to do.
So if you have 3
comparison.
runs of just gas or just air, and then 3 runs with your greenhouse gas, then you have the ability to calculate a standard deviation and see, did I get a significant difference, a statistical difference between my 2 runs?
Are we pulling all of our numbers from all 3 runs? Or are we doing standard deviation and mean for each run? And a
You
graph
can't-
for each run.
You can't do it for each run. You have to do it. So like you can do all of your air ones. You can calculate the mean and standard deviation for all
So,
of your air
okay,
ones.
so pull the air and then pull the greenhouse gas
Yeah.
numbers from all the runs. That's what I was
Just
asking.
from
I was
yours.
like, because that's a lot of numbers.
Yeah, no, because we're just looking at the change in temperature. This is our ultimate test, is the change in temperature. That what is the change in temperature? I mean, we're going to have a graph of a bunch of numbers, but what is the change of temperature for our air experiments for run 1, run 2, run 3? Do those 3, what's the, the average value? So,
So you,
Then
so we
what-
are going to have 3 means, 1 for each run.
no, because you're not calculating the mean temperature for your run. You're calculating the change in the temperature for your run. Let me pull up some of my data, because I took plenty.
That's what I'm confused about.
Yeah, no worries.
Because if we're going to do it for 20 minutes and we're supposed to take a thing every like 20 seconds, that's a lot of numbers.
It is a lot of numbers, but you may not need it that long. So like this is when I was doing a gallon bottle and I just was using like, I don't know, a pretty wimpy little light bulb, like a 60-watt bulb or something. So it wasn't a crazy high-powered light bulb. And so this was my first air run, this was my second air run, and then these were 2 carbon dioxide runs. And I plotted them all together, and then I normalized them so that they started at the same temperature. So I just added on however much to make sure they all started at 22.9, because all of them had a different starting temperature. And I wanted to see, okay, well, if I have this starting temperature and that starting temperature, am I actually seeing any kind of a change between any of these runs? And so you can see the blue and the orange, those were my 2 air runs. And they're right up here. They're probably a little bit higher than my 2 carbon dioxide runs, but I don't think they're statistically different from each other.
And then when you did your standard and deviation and mean, did you do it?
So I didn't do it,
Oh,
but what I would do is I would take and find the change in temperature. And that would be nice, Ronan. I will come and have some cobbler with you in a moment. Oh, okay. Can you put them in the compost? Okay, go ahead and have fun throwing them. All right, so I really want this one minus this one. Okay, so
final
that was my
minus
change in temperature.
initial.
Yeah, we're just doing final minus initial.
Okay.
Okay, and so these are my 4 change in temperatures, but these are only 2 different setups. So these first 2 are the air ones, and these second 2 are the carbon dioxide ones. And because I only have 2 runs of each of them on this particular experiment, I'm not going to do standard deviation, because standard deviation of 2 things doesn't really make sense, right?
Which is why we're going to do 3.
Which is why we're going to do at least 3. Now, I have other experiments. Can you see down at the bottom of my Excel file?
So when you say mean, you would want to be finding the mean like the 2 airs and then the 2 CO2 runs.
Exactly, right? So instead, so here's one where I did calculate it. All right, this one, I was using a LabQuest. So it just took the data for me, and I just looked at the final and the initial. So for these runs, this is all canned air. So these are all 5 experiments that are replicates. So on this one, I looked at the total increase in the temperature, and I calculated the average. So the total increase was these guys right here. Yes, Luna just told me that.
Okay.
So these guys are all the change in temperatures for the 4 runs, and this was the average and the standard deviation for this particular run.
Okay. So that's what you meant by mean. You meant like the mean between the 3 runs, between the change in temperature, and then the standard deviation associated with that change in temperature. Okay.
Great, thank you.
That makes sense now.
Yay! I know, I thought, oh, do I need to make a video for this one? I just don't have the energy this time. So I'll answer questions instead. But yeah, now I'm going to show off all of the runs that I did. I'm not sure it's a good kind of show off. It's a, Look at all my agony. So I'm not even sure this is all of them. So this was some runs that I did of a 60 watt bulb with air. And then, oh, that one didn't get in here.
Again, I don't have a light bulb. Like I really need to get like a desk lamp. I don't have a desk lamp. I got a flashlight.
Yeah, you can try using a flashlight. I don't know if it'll have enough power.
Can I just take it outside? If I do it outside, would that be enough light?
You can try it. I don't know because I haven't tried it, but
My desk lamp broke.
if
I
it's a
don't have
nice
one.
bright day, then it seems probable.
Mm.
Or just take one out of your lights at your house and then put it back.
I don't have a lamp at all. Like the one desk lamp I had broke, and I
Light-
borrowed it from my mom.
If you can get up to campus, Peggy could give you a clip lamp. You know, like one of those ones for light for
I might just go buy a new one. 'Cause I
okay.
don't mind having one. Or I
Fair
could go to
enough then.
my parents' house and be like, "Can I just hold the bag under your?"
Like, what are you doing?
I'm playing with greenhouse gases.
Yeah.
And it's funny because when I was younger, my dad was a mechanic and he did a lot of AC work. So I used to see him with all the pressure valves. And he
Oh,
was always like, "Don't let the Freon leak out. Don't let the Freon leak out." I'm like, "I don't know why you're saying that."
Now you do.
Now I know. He's like, "Because the EPA will get mad at us."
Yeah, that's the reason, right? Yeah.
Well, you know, he was a mechanic for 20 years and he's in his 60s. So that was a long time ago.
Yeah. Yeah.
Probably back when they were just figuring out that stuff was bad.
Probably. Yeah.
All they knew is the EPA said, "Don't do that."
Yeah. But now we know why. All
I'll
right.
just- I'll go
so
buy a new desk lamp. Does it need to
Okay.
have like a 60 watt bulb?
The 60 watt bulb is fine. If you want to use a higher power one, you can.
If I could find a clip on in the store.
Yeah, I mean, whatever, right? There's
I'll figure
lots of different. It just all you need is a light that will hold in one place in the same distance away from your experiment because you want that to be one of your, controlled variables, right?
Yeah.
So
Oh, I bet you I could get one that clips for like a chicken hatchery.
yeah, you could do
Chicken
that.
babies. Chicken babies.
Yeah. Yeah,
Is
or
there a thing?
a plant light.
Oh yeah. Okay. I'll go figure something out. I'll go to the store and go hunting. I need a light.
Okay.
Gotta jump off here.
All right.
See you
Yeah,
later.
it's 8:15, so
Um,
we should call it quits for tonight.
when you were going over the quiz, the scans came out all right, right? You could read them.
Yeah, I could read them. I mean, it was a little bit like the contrast was a little funny, but I could read
Well,
them.
when I do the magic color thing that you told us to do, you can't see my writing because I use a pencil. So it's like it gets bled out of the picture.
Mm-hmm.
So I try to keep it in that yellow because